One. In this check-in video, I'm going to talk about implementation of standard backpropagation using Python. This is the kind of network that we've been looking into, and I have given one of the assignments. In the assignment, um, there are a number of questions related with the use of standard backpropagation. The first question is about the feed forward and the backpropagation stage. We are only going to implement that in in one step, um, that is feed forward of the signal and then backpropagation of the errors. In question 2, this is a more like a complete problem where you are given with a training data where you have a number of input vectors or samples and the corresponding target values, and we are asked to train a neural network having 10 input units, 4 hidden units, and 2 output units using standard backpropagation. We will be using bipolar sigmoid activation function, and we will be randomly choosing weights, um, and the learning rate will be zero point 0.5, and we'll perform uh, 5,000 to 50,000 epochs and see how the weights are converging, how the mean square error is converging. So taking this as an example, I'm going to show you how to write down program in plain Python in in plain Python using NumPy and Matplotlib. So I'm going to open Colab. So I go to the Colab and just open a new notebook. And right now there is nothing in that notebook. I'm just going to add some text at the beginning telling what this video is all about. So it is check-in video 1, and it is about standard backpropagation. I can highlight it. Basically, what we are going to do is we are going to follow certain steps. So the steps that we are going to follow, I'm going to just write them down here. So steps are like, the first step is we are going to load data and do the initialization of parameters. In the second step, we are going to apply the feed forward process. Feed forward of the signals, you can say, because we will be send the signals in the forward direction. And then we have in step 3 we'll be using the backpropagation of errors. In step 4 we'll be updating the weights. And you can say, roughly speaking, in step 4 we'll be checking whether we have reached the convergence or not. So the convergence check will be made. Convergence check. Okay, so these are the steps that we are going to go through while implementing. At the beginning, I'm going to start off with importing the libraries, the necessary libraries. So I'll just write down a comment here: import necessary libraries, and the ones that are needed are, the first one is, okay, this is not going to be a comment. Import NumPy. Let me abbreviate it as NP, because I'll be using it in a number of statements. So writing down numpy at every statement becomes a little time consuming. And then from matplotlib, I'm going to import the pyplot as plt. I'll be using that for plotting things. I'm going to do is I'm going to initialize the random number generator, because we are going to generate random data for initializing the network parameters. So for that we need that. So initialize random number generator, and for that I will call numpy, and from that I will call random, and random has got this default random number generator, so I will call that default random number generator RNG with a seed value of 10. So I'm calling it RNG, my RNG. So I'll be using this to generate random numbers. So what we are doing is that when I run this program next time, it will start with the same sequence of random numbers. So the program becomes reproducible. So your results will become reproducible if you run them on the same compiler, on the same, for example, if you run it on Colab, you will get the same results as I'm getting here. All right. Before moving further, we will need some helper functions. So let me define those helper functions. And the first one is, of course, we've gone through a number of helper functions before. So the first is the activation function. So let's call it activation func. Okay, and it requires only one parameter. So this is the standard way of defining a function in Python. So I'm just going to comment it that the kind of activation function I'm using is bipolar sigmoid, and it will return from the bipolar sigmoid. I will take okay, so bipolar sigmoid will return only we've seen it before, so it's the division of two kind of exponentials. So we have one minus, and for using the exponential function, it is a function of the numpy library, so we'll call it from that. So we'll call specifically that function from numpy, and in the denominator we also have the same with a plus sign, of course. So this is how we are defining the activation function. We also need to define the derivative of this activation function. So let me call it D activation function func, and this activation function will have as its input the value that we have obtained from this activation function. So it will go there, and then we can find out the derivative from that. So this is the derivative of the bipolar sigmoid, and it is if you do the calculation, it comes out to be 0.5 times times 1 minus fx, the value, the input argument, times 1 plus fx. Okay, the multiplication here could be matrix multiplication. This x could be a vector in this case. So when we call exponential here, it will calculate the corresponding exponential for each one of the elements of the vector there. So the result will be a vector, and it is being divided by another vector here, 1 plus exponential this. So it's a vector divided. You know that we don't have a division of matrix by a matrix or a vector by a vector, but in Python, or specifically in NumPy, when you do this kind of division, then each element of the corresponding elements of the vectors or the matrices, they get divided. So this division operation is going to act as an element by element or value by value of each one of those vectors. Same is the case here. When I do the multiplication here, then fx could be a vector here. So the result 1 minus fx will be a vector, and when I multiply it with another vector with this direct here, then the result is a vector having got the same size, because the corresponding elements of both the vectors, they will be multiplied. Okay, so this is what we have for the time being. Now we need to define two important functions, one for feed forwarding of the signals, and the second one is for backpropagation of errors. So before I do that over here, let me move on and write down the rest of the program and see what are we going to do there. So just I'll leave some space here and come back here. So let me put some markers here, maybe some space for other helper functions. Okay, so I'm going to leave that over there, and then I move on to the actual running of my program. So I'm going to load the data as my first step. So as you can see, the first step in running of my program is loading the data. So load the data, and I have written it separately. I don't want to write down each and every value here, so that will be time consuming. So I'm going to write, just copy that over here. This is the same data that is given in the problem set that we are trying to solve from the assignment 1. So you can see that it's the same data, the input and output data of the assignment question number 2. So I'm using the same data here for this particular problem. So we have samples here, an array of samples. This is in fact written in the form of a matrix, and another matrix of target values. Each row of the sample matrix is made up of the samples. So this is sample 1, this is 2, 3, so on. For defining arrays or matrices in NumPy, you use numpy.array, and within parentheses you can see I have square brackets specifying that I'm going to specify an array, and then each row, there are multiple rows here. Each row is comma separated, and each element in that row is comma separated. So note these things, that this is the way you are going to load data. You can have this data stored in a text file like CSV files or other formats, or an Excel format, and you can load this data from those files also. So those are also the possibilities. Same is for these target values. Now once I have done this, what usually people do is that we split this data into training and testing sets, but we are not going to do that. So for this case, we will use all data as training data. So this is what we are going to do. The next important thing is initialization of the parameters. So I have written it separately, so I'm just going to copy those parameters and show you. So initialization of the network parameters, like learning rate, we have kept it fixed. We will be running some iterations. So what is it? Maximum number of iterations, you can have any number here. I've just put some number there. And then the maximum tolerance that we want to achieve as far as the mean squared error is concerned, we want a small tolerance, so I'm keeping it as 0.0001. From the samples here, I can find out how many samples are there. So if later on you want to change this data with some other data, then all you need to do is to change the data there, and then you can call this shape function, which is very important function in the use of arrays, especially in NumPy. So you can use it to find out how many samples are there, so how many rows of this data are there. I've specified 0 here, which means that I'm interested in the number of rows. If you specified 1, then it means you are looking into the columns. And for higher dimensional um, data, you have more axes in that case. Then I have the number of input neurons, Ni, it is 10, that is given in the problem. Number of hidden neurons is 4, number of output neurons is 0. So with this, we are all set now. So if you look back at the network, the network is like this. We have 10 input neurons here, and we have 4 hidden layer neurons here, and only 2 output neurons here. So accordingly, you can see that how many weights and biases should be there in this layer, layer number 1, and how many weights and biases should be here in layer number 2. So in this layer, the biases, you can see that they will be 4 because there are 4 hidden layer neurons, and the biases in this second layer will be 2 because there are 2 output neurons. And similarly, the number of the weights will be 10 times 10 by 4, and then 4 by 2. That's a kind of equation that we are looking into. Okay, so we will define these weights as the next step. Well, we'll initialize those weights, and in the problem it is said that use a range from minus 0.5 to plus 0.5. I'm using a range from 1 to plus 1. You can change that by changing the values here. This is the minimum value, this is the maximum value. So actually this is like defining a range. So if you are interested in some random number x, which is from range a to b, okay, so you use that b minus a, and then times you call the random number generator, and then you tell how many random numbers you want to have there. Okay, so basically when we look back here, I defined this, I initialized this random number generator, and I'm calling it RNG. It is beginning with a seed value of 10. There are different types of behaviors of the random numbers. We can have shuffling values. We have different kinds of behaviors for the random numbers, but we are using the default one here. You can play with this later on and see how many different kinds of random number sequences that you can use. They become important as you go more into solving problems using probability distributions and other. So, but for the timing, I'm sticking with the default random number generator, and with some seed value here. You can use some other seed value, okay? But if you use the same seed value as I'm using and same code, you should be getting the same results. If I change the seed value here, then the results will be convergent, but the behavior will change because the starting value, the starting random numbers will be different. The weights and biases, they will be different. So bias 1 and weight 1 are for layer 1, and bias 2 and weight 2, they are for layer 2. So they are going from -1 to +1 in this +1 in this case, and I'm calling this random function of random number generator, and I'm specifying how many random numbers I want. So I want 4 times 1, so 4 random numbers, 4 by 1 random numbers, you can say, and we want 4 by 10 random numbers here. Similarly, in the second layer, so we are defining these weights. We are initializing the weights and the bias in using the random numbers. So once we are done with this, we can begin with our iterative loop. So I can write down for itr, that is the index for the loop, and I want to change the values, take the values of this iteration from 1 to, say, maximum number of iterations, which I've defined here, by the way. So let me just copy it from here and put the value there, okay, and colon that ensures that I go to the block of the for block. And I define the maximum error. I initialize it to 0. Once I'm done with that, then I'll pick one sample at a time from my data set. So I sample in range from 0 to n samples. So I'm picking one sample. Let me call that xtrain. So the first sample is from samples, and it is I sample. Okay, the first sample, and I'm going to reshape it because I want to. You see, my data is in the form of rows. So in the network, usually you use input as a vector, a column vector. So it's a row vector. So I need to change it. So let me either I can use transform it, or I can use reshape function. So for reshaping, let me reshape it to of size ni by 1. So as there are number of inputs, so I'll just reshape, rotate this sample, and that will be my input training vector, and the output will be y train will be from the targets, and it is defined in a similar way. So I will pick I sample and all the values from that. There are only 2 in this case, and I'll reshape that 2, and in this case it will be according to the number of neurons in the output layer by 1. So it will be basically 2 by 1, and this will be 10 by 1 vector. So now I've got my data available here. Okay. So as soon as I've got my data available, I will be calling a function which will do the backpropagation. So let me call that function, and I'll call this, let me name it back prop, and I'll send in some information to that. So what is the information required for backpropagation? Now for that we need to revise our theory a little bit. So let's go back and see the relevant theory. So when we are looking at this network, so there is a layer of input neurons, there is a layer of output neurons, and then a hidden layer. So there are 3 layers. In kind of block diagram, I can show it like this. So you have input layer, hidden layer, and the output layer. These are the biases. The input which is given here, it is of size ni times 1. So it's a vector. I'm calling it x. And then there is a weight matrix here because of all the links, which I'm not showing here, just representing it with this matrix. And there are bias. This corresponds to the bias vector. So again, all the links which are going into the hidden layer, they are connected with this bias. So this is as far as the first layer is concerned. So this is weight matrix 1, and this is bias vector 1. For the second layer, we have weight matrix 2 and bias vector 2. The way they have been their number is like nh by ni, and no by nh, and over here I have no by 1 and nh by 1. So these are their sizes or dimensions. Now when we apply this weight matrix to this weight vector, so we do this kind of weight multiplication. So we have a matrix here, we are multiplying it with this vector. That will be that will give me the dot product of these. In fact, that is the total input which is reaching at each one of the units here. So there are an h units here. So for every unit, I'm making this matrix multiplication. So the weight matrix is being multiplied with this x, and we will add it. The resultant will be a vector which is of size nh by 1, and we'll add it to this initial bias which was there, and this is the total or the net input reaching at the hidden layer. So it is basically the input to the hidden layer units, and it is the weighted sum of the inputs. So once we have got all those inputs available in this vector for each one of the hidden units, we pass it on to the activation function of this hidden layer. So the activation function for both the hidden and output layer, in our case right now, we have taken them as bipolar sigmoids. So this f is basically bipolar sigmoid. So we will pass on this array to the sigmoid bipolar sigmoid function or activation func as in our case, and we'll get the output of hidden layer neurons. Once we have the hidden layer neurons output, it will then flow, this information will flow through the second layer. So this was the first layer. So this is basically the feed forward stage that we are going through. We're going through this step and we get the outputs here. Once we get the outputs of the hidden layer, they are multiplied with the weight matrix here and the bias vector to give the net input reaching at, in a similar way, reaching at the output layer. All we need to do is to keep track of this matrix. It should be of the right size and it should be multiplied in the right fashion. So this matrix is basically rotating this vector towards it's making a projection of it. So it's that kind of thing that I discussed in the class. So we add this to the bias to get the net input reaching at the output neurons. So input to the output neurons is the weighted sum of the inputs which are reaching here. Once I calculate this, I'm calling it Z2, and then it's going to go into the activation function, the activation func, and we will get the output of this layer. This is going to be the output that we are getting as a result of passing on that one vector. So this is the feed forward stage. Okay, so let's begin with this first because this will become a part of our activity. So I go back and do this first, and then I'll go back to the backpropagation of errors. So in the first phase, I need so let me comment this for the time being, and in my helper functions, let me define. Now I left this space, so right before it, let me define a function. Let me call it feed. Let me call it feed forward. Now, what is required by this function? This function requires the input vector, and it requires the bias and the weights. So it requires B1, W1, B2, and W2. So these are the things which will go into this function. And then how we are going to go about calculating all the net input. So in the first place, we are interested in this. We want to find out the weighted sum of the inputs reaching at the hidden units. So that is basically Z1. So if I go back, I can show you that we have, sorry, so we have Z1 here. It is B1 vector plus, for layer 1, the weight matrix multiplied with the with the input. Okay, so that's what we are doing here. So you have the weight matrix, and we multiply it with x using the dot function of numpy. So numpy is basically we are making you, it provides a number of other functions, so dot is one of them which is used for matrix multiplication. So we are finding out the product of W1 with x, the matrix multiplication. The result will be a vector in this case because x is a vector. So when this matrix multiplies with this, we get a vector, and this vector will be added to B1, which is the bias vector. So the first vector that we have here. So it will get added to that, and the result will be the total input or weighted sum of the inputs which are reaching at the hidden neurons. After that, we will calculate the output of the hidden neurons and the derivatives. So that we can do here. So we can apply the activation function which we have here onto that Z1. Remember I told you that x could be a vector, so now Z1 is a vector. So we'll pass it on here, and it will find out A1 for us, which is the output of the hidden units. Okay, and we are also finding out the derivative of the activation function um, alongside, because we have this a1 available here, so we can pass it on to the derivative of activation deactive activation function, and we can calculate those derivatives. Now once we have those, we can, so this is through the first this is running through the first layer. For the second layer, we have, again, we will do the same thing. We will have W2 multiplied with what is coming out of the hidden layer. A1 are the outputs of hidden layer, so we'll multiply W2 with A1, and this is a matrix multiplication, and we'll add it to B2 to give us Z2. And then we will apply the activation function on it, and we'll find out its derivative also, just the way we did it for the first layer. So both the layers, so we are gone through the whole process of finding out the outputs at each one of these layers, and we were also able to find out what are the inputs reaching at those two layers. So we've got all the information that is required in the feed forwarding of the signals. We need to return that because there will be a function which is calling it. I have a bad tendency of putting semicolons everywhere because of working too long in C environment, so just pardon me for that. So we need to return in MATLAB, sorry, in MATLAB or in C or in C++, you need to put those as termination marks, but in Python, okay, if you put there is no harm, but customarily we don't use any termination mark. Okay, what are we going to return to the calling function? So in this case, our main function is the calling function, and we need to get all these values there. So I'll send all the values that which I have calculated, all those vectors which I've just calculated as a part of this function, to the calling function. Okay, so this is how it's going to work. So this is how the coding part of feed forwarding of the signal will be carried out. For the backpropagation of errors, we begin with the output layer, and at the output layer, we first calculate the mean squared errors. So the error itself is the target values that we have got for that sample, and we'll find out the difference of that target value from whatever y we are getting here. So we'll calculate this difference vector. I'm calling it epsilon. So this is, well, this is yeah, so it is epsilon. It's giving us the mismatch between the target and the output that we are getting, and this will be used in calculating the mean squared error by simply taking the dot product of these. So I take the transpose of this, multiply with that, it will get a single value divided by 2. That is our mean squared error. Once we have these two available, then we can find out the local gradients at the output layer. And in the formulation which I gave you earlier on, you can check out the notes. It is this difference vector times the derivative of the activation function. So this is where the derivatives are going to play their role. So I use a different kind of operator here, which is just showing that the matrix multiplication here in this part will not be on element by will not be like usual matrix multiplication. This is element by element matrix multiplication. You see, in mathematics, when we write down product of a matrix with a vector, we mean the way a matrix gets multiplied with another matrix. It's not usually on element by element basis, but in NumPy, this is when we write down a a star between two matrices, it means this kind of multiplication, element by element multiplication. For matrix multiplication in NumPy, we use dot function. So we in that function we give the first matrix and second matrix, and that way we get the matrix, the product of the two matrices. Okay, so we calculate this delta, the local gradient for the output layer, and then this local gradient can be multiplied with eta and the input which is reaching at that layer. So from that we can find the input of the input which is coming to that layer from the hidden units. So we multiply that to get the weight change. So weight change is calculated in this way for the output layer. For the hidden layer, we propagate these errors, these deltas, backwards. This is what do we mean by backpropagation of errors. So we have these deltas and we multiply it with the weight matrix 2 by taking its transpose, and we calculate the weights, the weighted sum of the weights, the weighted sum of the local gradients reaching at the hidden layer neurons. And then we multiply those with the derivative of the activation function for the hidden neurons and get the local gradients for the hidden neurons. So for the output neurons, it was straight away, it was easy. This epsilon was known and we multiplied with the activation function there. Here we know the activation function for the hidden layer, but we didn't know what should be the gradients. So to find those gradients, to find out those deltas, we multiply the local gradient at the output layer. We propagate them back through the links, which means that multiplying it with the weight matrix there to get the weighted sum of the errors which are reaching at the hidden units, and that way we calculate these local gradients at the hidden layer. Once we have that, then it is similar to this expression here, eta times the local gradient times input. So we calculate that way the weight change in that layer. So just keep those in mind, and I'm going back to the working on my backpropagation function here. So I'm going to write down the backpropagation function now. In fact, I wrote it down earlier on, so just to save time, I'm just going to copy some of the stuff from there. So some of the things that I require are so what the backpropagation function requires is the learning rate, because in the formulas we need that. We need the training vector, we need the x training vector, the inputs, and the output training vector, and we need the weight matrix, the bias and the weights for both the layers. Once we have that, then I'm just checking what is the size, what is the length of this training vector. I'll use that for normalization purposes, and then I will just use feed forwarding of the signal. So in backpropagation, basically you begin with feed forwarding of the signal. Instead of doing this all the steps again, I'm just going to call this function which I've just written. So I'm going to do this. So I'm calling this feed forward function with x train as the input and the weight bias and weight matrices, and I get all these weighted inputs and the outputs of the hidden layer neurons and output neurons, etc. Once I have got those, then I can calculate the error. Okay, so that is the mean squared error. Okay, so I'm going to calculate the error. Let me get rid of this now because I don't need that. So for mean squared error, I have written down that function. I'll write it down in a moment. So this function will give me the error for that particular iteration. So once I have obtained the output of for this training sample, the output is in the form of A2. I compare it with Y train, which is the expected output or the desired output or the target value, and using these two I calculate the mean squared error, and I'm saving it in some variable. Okay, once I've done that, I can then calculate the error at the output layer. Now remember, at the output layer we need that because for the output layer we use this, we multiply it with the derivative of the activation function there to find out the local gradient. So that is our next step actually. So after doing this, I'm going to calculate the local gradients or deltas at the output layer. So if you check this, this is simply the mismatch between A2 and Y train. This is your difference. I multiply this difference with dA2, which is the derivative of the activation function. Okay, 2 means that it is for the second layer, it is for the output layer. So I multiply these two with steric. Steric means here, you see in the notation I'm using here, I put this for element by element multiplication. In since both of these are vectors, numpy vectors, so or arrays, so I use this to get that element by element multiplication. So delta out will give us a vector of values for the output neurons. So these are now available to me. So once I've got these, I can calculate the weight changes or the weight update. Okay, so the weight update is, okay, so we can calculate the weight updates. So that is basically minus learning rate times the product of this delta out with A1. A1 is the input reaching at the output layer, well, input of from the previous layer. So we are talking about output layer, so input to that is coming in the form of A1. So we take its transpose, multiply it with delta out, and then we multiply it with the learning rate to get the delta W2 matrix. And for the bias, I do not take the dot product because delta out, if I multiply it with a vector of ones, it will give me the same value because the bias unit has got value 1 equal to 1. So A in that case is 1, is a vector of all values having 1. So I simply use delta out here. You see, I'm dividing these values by n. Okay, both of these values are um, divided by n. I forgot to put that over here. So in this way we can this is used for normalizing the deltas. Okay, you are at a liberty to check whether n is needed or not, but customarily we divide it, we normalize it. Okay, so this is for this is when we are calculating the local gradients um, for the output layer. For the hidden layer, okay, we follow a similar scheme, but it will be a little involved. See, we need to find out, in addition to uh, in addition to this, we need to find out the sum which is obtained by taking the matrix product of these deltas, which we have calculated here, these deltas, multiplied with the weight matrix there. So this is going to give us the weighted sum of the errors which are reaching at the hidden layer, and then we'll multiply it with the activation function, the derivative of the activation function. So that's what I'm doing here. I'm multiplying this W2 with the, since the information is going in the other way around, so I take the transpose of it. So delta out is multiplied with this, so this is matrix multiplication. So since delta out is a vector, so the result will be a vector, so we get these values, and then we multiply it with dA1. This is similar to this one, so instead of using dA2 here, I'm using dA1 because we are at the hidden layer, and we should use the derivative of the activation function at that layer. So once we have this, we get the deltas. These are the local gradients, delta head, so they are similar to delta out. Okay, and then we use these delta head with the training data in this case to find out the product and multiply it with the learning rate. I'm dividing by n to get delta W1. Similarly, delta B1 is obtained by multiplying the learning rate with the delta hidden. So, and you see that in both these cases we have a negative sign here because we want to do gradient descent later on. So our weight updates will be in the negative direction of the weight, the gradient. So that's why we have these negative signs there. Okay, so this is over. With this we come to the completion of backpropagation. What needs to be returned here? So what are the things that we want to return? Of course, we need all these delta, the weight changes that we have just calculated, because those are the ones which are, so delta B1, delta W1, that are coming from here, delta B1, delta W1, and similarly delta B2 and delta W2 from here, and the error, mean square error. Okay, so these are the values which will be required by our calling function. Now, mind you, I talked about this before. This ms error, mean squared error function, was not defined, so let me define that also. So define ms error, and it requires two values. One are the predictions, so let me call it y predict or prediction or predicted. That is the y predicted, and then the true values, the values which are uh, the ones which the exact values or the target values. Okay, and here again I need to calculate the difference, and I multiply it with itself to using a dot product here. Here you see, if I take the transpose of this vector, I get a row product, a row vector. So product of a row with a column gives us a number, and then I divide it by 2, and I also divide it by the number of entries there that were there. So again, this is kind of normalization. It's the same n which is used there. So this gives me the mean squared error. Now, now I am in a position to call this function. So let me call backpropagation function. Okay. So I come down here. So in this iterative loop, I am going to call this function, and the return values will be there. So I need to put those return values. So let me put this all in one. Um, okay, like this. Probably this will be a better way. So I'm calling backpropagation with the learning rate. X train and Y train will go in with the weight matrices, and then we will get the weight updates along with the error. So that's what this backprop will do. Once I've got these values back, I'll make a check how much the error is. So if the error is greater than max error, then I will set max error to this mean squared error. Now the reason being that over here I initialized it to 0 before going into an epoch. This for loop corresponds to an epoch where I go through all the samples one by one. So before I go into the epoch, I calculate for every sample which goes in here, I calculate the error, and if this error and then I work out which is the maximum error out of for all of those samples. Okay, so this max error is being used for that purpose. So at every iteration, at the start of every iteration, I initialize to 0, and then I check if the error that I'm getting from my backpropagation is more than this, then I will make that maximum error. Okay, so this way I'll keep on checking what the maximum error is. Next step is, of course, a weight update or weight change. So we'll do that weight update. Okay, now this will be a part of this loop. Okay, later on when you want to do this problem using um, in a batch mode, then you have to move this somewhere else. Right now I'm doing the weight update in every with every sample, with every um, um, well, with for every sample I'm doing it on sample by sample basis. So it's pattern by pattern approach. So it's not, it is stochastic approach which I'm using. Later on I'll use I need to use a group approach, where a batch approach, then I'll need to put that somewhere else. I have to keep track of how much was the weight change and then do that weight change later on. Okay, so that is a part of the next question, I think. Now this is as far as this loop is concerned. This loop will finish here, and then I move on to checking. Once we've gone through all the samples, I'll check what are the, so after this I'm going to check. So you see my if statement here is now not indented. This is has got the same indentation as for this loop, so it means that we are in the outer loop here. So we are checking, after going through all this, we'll get some max error, and we'll checking if this max error is less than epsilon. Epsilon was over stopping criteria, so we are checking if that it has gone down or not, and if it has, then we will write down that our iterations have converged and the maximum error was that. And I'm also keeping a track of how many iterations were in how many iterations we were able to do that, and we'll come out of this will break out of this for loop. Okay, so once I'm out of all this, I can write down on screen. um, Once I come out of this, then I'm out of the outer for loop, so I can write down checking whether if number of iterations was equal to or greater than max iteration, then we'll say that maximum iterations have reached. But in both cases, we are going to write down the number of iterations, maximum error, and the value of the epsilon. So these are the things that we are writing down at the end. Let me run this. This loop will this whole will run for a large number of iterations. So let me reduce the number here. So let me say that I want to run it from 1 to 2 for a single iteration. Okay, just to check whether my code is working or not. Okay, so all I need to do is to run this. Hopefully I won't get any error. Let's see. There is an error. Ah, yep. Again, I should use a so running it again. Instead of using colon, I should use a comma there. See, after so many years of using Python, you still stumble upon, especially when you keep on switching between languages, then this happens. So it has run the loop. So you see maximum error was this and epsilon is this. This is after one iteration. Epsilon is very small, the error is more than more than one. So let's run it now for say um, 1 to 10 iterations. Let's see what happens. Again, my bad. I have a strange habit of putting. So when I run this, maximum error is lesser than that. Okay, so the error is coming down. I can put actually a some print statement here to find out what is the iteration number and maximum error, so that I could have some feeling of how the error is changing. So let me put some print statement somewhere here. Okay, so I want to see how the errors are propagating. So I just want to see if what was the maximum error at that iteration. So for 10 iterations, you can see that it started off with 1, and then the error, maximum error, is reducing. And if I go to 100, the error is reducing, of course, it's going down. So I don't want to write down all these maximum errors, so let me comment it back. Oh, not this one. The print statement over here, and then let me change back it to, let me revert back to this from 1 to max iterations and run it and see what do we get. Do we get some solution or not? See, it's taking longer than required now because it's going through a more number of iterations. So it is still executing. We have reached convergence. So after 19,259 iterations, our solution has reached the convergence for the design criteria. Okay. Now one more thing that we can do at this stage is to see visually how the error has got reduced. So for that I need to add some I need to store some information. So we have been calculating this error. Okay, so let me store this error somewhere so that we can use it later on. So not only that, but also I need to store some other information for plotting purposes. So um, let me go to the beginning here before the iteration start, initialize something. So I'm initializing x-axis and error for error plot. I'm so using the zeros from NumPy, um, maximum number of iterations. So this is a vector of that many values, 0 values, and the other one is another vector. So once I calculate uh, the value of the error here, okay, over here, then I can store that value. So I can store both the I can store here right after calculating these weights and everything. I can store the values of iteration number into the x-axis iteration and max error in here. So now I will have all this information available to me for plotting purposes. So I can use my plotting function to do the plotting for me. That's why I included matplotlib at the beginning, because I wanted to see how it looks like. So at the end of my function here, I can include these statements. So these statements mean these are just the same statements that I've been using for plotting the activation functions, the other um, notebook that I've shared with you guys. So you can have a look into that. So here I can plot these results on a linear scale. So error plot will be plotted on a linear scale, and we are just going to have a look at how does it look like. It's going to take a few seconds to go through all the iterations again and then produce those results, and I should be able to see them once it is done. The execution has taken about 12 seconds. So okay, this graph is not that informative because you can see that the value goes down very quickly, okay, and it becomes very close to zero. So in very small number of iterations. So nothing of that value is available here. So let me um, uncomment and try to plot it on a semi-log scale. So which means that I'm using a logarithmic scale along y-axis for the mean squared error. So that's why I have the x-axis. It will go from all the terms up to the iteration where it got interrupted, where the value became less than the epsilon value, and we are using the same y values for the error values. And let's see how it looks on a semi-log scale. 3 seconds, 4 seconds, you can see that the seconds here, 9 seconds. It's going through backpropagation now, and it's almost done. And now you can see this is a better picture than before. So you can see that the error goes down from a large value near 1, more than 1, and then there are some kinks here, and then it goes down to the required 10 to the power minus 4, less than 10 to the power 4, around that many iterations. Okay. If I plot both of these on a log scale, that I can do also using a log function here. So on a log scale, it will look like this. Again, it'll take a few seconds to complete. So about 12 seconds or so. Yep, 13 seconds. And you can see now this is more informative because both the scales are logarithmic now. And as the number of iterations go from 0 to 1 here, then 1 to 0 to 10 here, 1 to 10 here, and 10 to 100, and then 100 to 1000, and then 10,000. About that place we are getting the convergence. Okay, so definitely the errors are coming down. Over here we have some local terrain issue, but the convergence has reached. Okay, now one thing that you want to see is whether you have really achieved the convergence or not. We have reached the convergence, but is our trained neural network giving us the results that we require? How accurate our trained network is? So to find out the accuracy, so there are two things. We have looked into the errors, mean squared errors, but how accurately it was able to classify the data that we have given it. So for that we need to pick one of the data randomly from our samples. So any one of the sample at random from here and its corresponding target, and send this information through a feed forward function. So just one pass treatment, signal passes from the input towards the output, and we get the output, and then we compare that output with the corresponding value and check whether it works or not. Okay. Now we are going to test whether our network has really converged and it is accurate enough. So for that we can run some tests. So this is one sample test. What I'm doing here is I'm selecting a sample from my training data, because my training data is the only one which I'm using. I don't have any testing data. So I'm picking a sample at random from here, any sample and its corresponding target value. So I'm selecting a sample number at random. So I'm using again random number generator. This will give me a random number in the range from 0 to 1. I multiply it with 7 and add 1 to it. So the number, since there are 8 samples, so this number should come out to be between 1 and 8. So this number will always be between 1 and 8. And I convert it to integer because it will be in the form of a floating point. So I get this sample. I print it on screen what is the sample number, and then I pick up the data the way I was picking up data here in the loop. Okay, just exactly the same way over here in the iterative loop, where I was picking one sample at a time to do the training. So I pick that corresponding data, the training vector, which is the input vector, and the target, which is y trained. So I've got both of these now. So I will pass this x train to my train network. So I'm sending that in over here, and then I calculate the results, and you know that the last value that is obtained here is the prediction, is A2, which I'm calling y predict now. So this is the one which should be compared with the target value. So then I'm simply plainly printing both of these, the target that is required and the one which I have obtained, the output that I have obtained. So if I run this, let's see what I get. So you see sample number is 7, and as a result of this I'm getting I can run this test again if I want to, and let's see, since the seed is the same, so I need to shuffle the data. I can choose some other sample number, say sample number 3 here, and see whether that one works. So sample number 3, you can see the prediction and the training, they correspond to each other. I can select some other sample number 1, for example, see if it is working for the data. So my network is trained. It is giving me correct results for each one of them. So I will go through all the training data and check whether there is a mismatch or not. And if there is no mismatch, then my network is giving me 100% results, which in this case you can verify on your own. So I hope this video will help you for implementing the program. You can stop it at certain times and see how I'm doing the coding, and all I want you to do is to write down yourself and see. I'm not using any specialized library at this stage. I'm not using TensorFlow or other libraries, PyTorch, etc. I'm using plain Python along with NumPy, and for plotting purposes Matplotlib. So that's all that I'm using. Okay, for help out about NumPy, you can go to numpy.org. Okay, and a lot of material is available there. Okay, there are open. This has got all the information about the library, about various case studies, and it has got documentation. You can go to the documentation and see what kind of documentation is required, okay, for the beginners level, for other users, etc. So for absolute beginners, if you go there, it will give you information about, it will start from that, but it's better to go for the fundamentals. So how to create arrays, how to convert those arrays. So you can find out all the information about NumPy there, and all the information about Matplotlib is also available there. So if I use matplotlib.org, I go there and most of the information is there. Again, you have examples, you have tutorials, you have different plot types. If I go to examples, there are large number of examples covering a vast area of how to plot with the source code available. For example, I wanted to plot in today's tutorial, or in the check-in video, I wanted to make use of logarithmic scale. So you can find out all that kind of information here, how to change the axes and how to label, do the labeling, annotations. So you can have not only the plots but also the source code given with them. You can have in a single plot you can have multiple graphs, etc. So I hope this will be useful, and let me know um, how good this was, and whether this was helpful to you or not. Best of luck.